So this room is session 1B, top-down exploration of climate effects on the coastal temperate rainforest. My name is Tom Ainsworth. I'm with the National Weather Service office here in Juneau, and together with Eran from the University of Alaska Southeast, we're co-chairing this session. The idea of this session is to talk about the interdependency of all the physical and ecological processes going on in the temperate rainforest. For those that were on the cruise yesterday, you got to see that firsthand with from the ice down to the water life and everything in between. So today's talk is to touch upon a little bit how delicately balanced each of those ecosystems are. And we're going to talk all the way, the top-down notion is from the atmosphere down to the ocean. So I'm going to just introduce very briefly who the four main speakers are for this session. They'll be coming up one by one. After they have done their 20 minutes or so, the next speaker will come up. If you have a burning question, it's okay to answer that or ask that at that time. But you are very involved at the end of this session, and that we want a lot of audience participation, and we'll have a panel discussion for the last 20 minutes or so. So as we've been talking as a group for this session, we're trying to motivate action, and I think you're seeing that as sort of a bubbling theme here, is to, like the one student said so nicely right at the end there, how do we do more than learn but take some action? And so hopefully our session here will give some ideas, some thought-provoking ideas, and take it from there. So very briefly, we're going to lead off here with Nicolas from the University of Washington and NOAA, wears two hats. He's also the state climatologist for the state of Washington, and he's going to be talking about the atmospheric side, the ocean-atmosphere linkage, and Nick has done some research up here in southeast Alaska and a good friend of the National Weather Service. After that will be Motyka from the University of Alaska, professor of geophysics, talking about the ice side and the geology side a little bit. After Roman will be Paul Hennon from the Pacific Northwest Research Center, getting into the green sides of the hillsides, forest life. And then last but not least Phil Mundy from the NOAA Ted Stevens Marine Research Institute here in Lena Point in Juneau. And he'll be talking about the coastal interaction with the forest. So again, we'll go from there, about 20 minutes each. If you have a good question right away that you can't wait for, go ahead and ask it. Otherwise, please be ready, like I ask my kids every day before they go to school. Ask hard questions today. And so that's your role when we get wrapped up here. So thank you very much. Nick Bond, all yours.
Yeah. Oh, there it is. I'm not sure what I should really add to this cartoon, but presumably it's like all good satire, is a little too close to the truth to be entirely comfortable. But anyway, what I'm really here to talk about is some of the climate signals that are emerging for this area, what we're getting out of these, the global climate models in terms of suggesting what's going to be happening over the next couple of decades. And in particular, how that's going to be impacting the coastal waters of this region. I'm a meteorologist and climatologist, but I work a lot with oceanographers, and a lot of the work that I do has to do with how the climate variability and climate change affects the marine ecosystems of Alaska. So that I'm showing my kind of true colors here. Another reason for doing this is that the ocean and the atmosphere around here is so strongly coupled. Here are two time series of sea surface temperature in the kind of green color right offshore of Alaska versus the air temperature at Sitka, Alaska, going back the last 60 years or so. And especially in the second half of the record, you can see how tightly coupled the year-to-year and kind of multi-year variations in the record are. And as kind of an aside here, early in the record, I'm not sure I trust those SSTs. It was before the satellite era when we got a lot of good measurements of that. And so that it was so warm in the late 50s, I kind of really wonder about that. So I'd like to start off first with just very briefly setting the stage for what are the kind of climate drivers for the area. And in particular, there's on the left-hand column here, there's the main mode or kind of pattern of variability for the North Pacific as a whole called the Pacific Decadal Oscillation, or PDO. To some of you in the room, this may be a familiar acronym. If not, that's okay. Essentially what it is the main source of kind of year-to-year and decade-to-decade change in the atmosphere and ocean for the North Pacific. We know that the climate isn't static, but it varies, and so it's important to kind of have those variations in mind when trying to look at climate change. So in particular with the PDO, when it's in its positive phase, there's lower pressure than usual in the vicinity of the Aleutians, kind of counterclockwise circulation or cyclonic circulation in the winds. The ocean is warmer than normal along the entire west coast of North America up into the Alaska Peninsula. And there tends to be, the currents are stronger out of the south along the coast than usual. This is not just of academic interest. It turns out that the prosperity of the salmon stocks is closely related to this PDO, and that when it's in the positive phase, Alaska stocks tend to do better, and the lower 48 stocks tend to do worse, and vice versa. And so that was, up until about 10 years ago, that was how we thought of the main source, or how we thought about climate variability in the North Pacific in this region. But in the last 10 years, something has emerged, that right-hand column, the NPGO, kind of proliferation of these acronyms, the North Pacific Gyre Oscillation, and there, that instead of just higher or lower atmospheric pressure and a response in the currents and that sort of thing, it's more of a dipole with a yin-yang to the north and south, and in its positive phase, lower pressure to the north, higher pressure to the south, stronger west winds bringing more water into the west coast of North America, and both stronger currents from the north along California, the California current system, and from the south in Alaska. And so we've got we're simpletons once removed. We have two kind of primary modes of variability here to kind of keep track of the system. So this is how it's like a drum head and how it fluctuates. And so these are the natural variations in the system, and in any sort of analysis of climate change, you have to take into account that the system varies and is going to continue to vary. So in looking at those, in trying to anticipate those changes, we have a bunch of models from different modeling centers from all around the world that are contributing to reports from the IPCC, the Intergovernment Panel on Climate Change. You can't see this as just kind of a laundry list of the ones that were produced about, created about 10 years ago for the last report. There's a whole new set of models for a new report just coming out. They have different strengths and weaknesses, and for North Pacific purposes, it is probably important to take into account that not all models are created equal, and some are probably better suited for looking at the changes that are going to be occurring in this area. And so I've been involved with a lot of, with some other folks about looking the big kind of map on the right. That's the observed pattern of variability with the PDO. This is our main mode of variability in the Pacific, with when it's warm in the the east it's cold in the west and vice versa. And to see how these models do in hindcast simulations, or backcasts, I think was referred to this morning, for the 20th century, how well did they replicate the observed climate? And roughly about 2/3 of them do a decent job, not a perfect job, but a decent job of reproducing the observed variability. And those are the ones that we think that we can use, are more reliable for looking into the future. When you use, at the time I made this chart, there were 10 of them available. I used the best 10 of these models, and here are time series of changes in temperatures for those various boxes across the various parts of the North Pacific, kind of color-coded there. These are model ensemble model means. And so this is, these trajectories in temperature are not what the climate's going to do. It's going to continue to have these variations. It's just what the models are predicting as a group. And one of the important things to realize here is box 1 is the red box, or the red line there, and it has a relatively rapid increase in temperature here as predicted by these climate models. But our variability in the conditions around here is relatively high. And so really the best way of kind of looking at the changes is to kind of say, how soon will these climate trends, these upward trends, kind of get us into uncharted territory? And I think it was referred to earlier today that essentially the normal years in the future are going to be like the very most warm years now. And so here, this gives you a measure of when at least the upper ocean temperatures, what year in the 20,000s is going to, or 2000s, is it going to be kind of uncharted territory? And here we have maybe a little bit of luxury of, we have so much variability in the climate system that we're not going to see a huge change relative to that variability, at least for a few decades. Want to take a little time talking about some work I've been involved with, focusing on the coastal Gulf of Alaska. And one thing that's arguably a problem, but maybe more an opportunity, is not a great deal of work has been done looking at climate change in this area. And so I'm interested personally in pursuing that more. And as kind of an aside, the reason I'm coming here is to look and see where we might develop some partnerships. And I say that knowing I should have more sense than that, and it sounds like work, extra work. But I'm actually serious. I'd like to see where there are kind of opportunities, low-hanging fruit that can be exploited. And I think some of the work that I've done in the past, looking at some of these issues, kind of, I'm probably able to kind of step in and perhaps help in without undue effort, hopefully. Right. Anyway, so in the Gulf of Alaska, what it turns out is, at least, especially if you're a pink salmon, what really matters is the conditions along the shelf, and when you the first few months after you emerge from the estuaries and are out there mixing it up with the big bad world. And there, it turns out that how fast the currents go along the coast there are related to the winds, and how the structure of those currents along the coast, or the ocean structure, is related to how much freshwater runoff there is. And that's a key property of that system. One thing that these models don't do very well is get the precipitation, and in particular the melting of glaciers and the runoff from the coastal streams in this area. They just have way too crude a representation of all the physics that's going on here. And so we can't rely on them explicitly for that. But in this little panel here on the right, what I've done is some work, and I looked at just time series of that freshwater runoff estimated for the Gulf of Alaska as a whole, versus the north-south component of the winds, and found out that indeed, and this makes a lot of sense, is that when the winds are stronger from the south, there's more runoff. There's more warm, moist air coming in from lower latitudes, raining harder. It's higher snow levels, and so it's coming out as water rather than getting bottled up in the glaciers or in the snowpack. And so this is for the late summer months, but this is an example of, in some cases, you can tease out some of the expected effects in climate change indirectly. And so I've been involved with some efforts of that sort in various places, the Bering Sea, along with the U.S. West Coast. What I've done here is looked at, again, at these climate models, and I want to see, okay, we think that how much fresh water is coming out of these streams, and perhaps due to melting glaciers, perhaps due to precipitation, is related to the winds. What are the models saying for these winds? And here, using a collection of the ones that were rated the highest, the mean of those, and I even tried to weight them, better models got a little higher weighting, is in red with the time series out to 2060 or so. Individual climate model runs are these other colors. And so the actual climate is going to still continue to fluctuate up and down. In this case, it's just a measure of wind. But the screaming message I want you to get across here is we're not anticipating big changes in the winds, in the kind of pressure patterns, those storm tracks and that over the next few decades. If you actually look at the same thing as kind of what the north-south or a long coastal component of the winds also, whether it's going to be reinforcing the Alaska coastal current or suppressing it, not much change with respect to the variability. The same thing is, I've been looking just recently at some of the very latest climate model results. Here is for the ocean circulation itself. This is kind of, I know, a confusing figure, but what it shows is these are streamlines. The closer the flow in the ocean is parallel to those lines, the closer they are together, the stronger it is. The black lines are what this particular model is, a very state-of-the-art one out of the Canadian Modeling Center for what it's worth. What it shows for the kind of present climate versus the future, and really pretty modest changes in this, the gyre circulation. So we're not looking at really big changes in the winds and the ocean currents, but we are, again, just at the, like at the sea surface temperature, anticipating fairly dramatic changes in the temperatures, and conceivably of here, this is one of the parts of the world that we're expecting greater amounts of precipitation in the runoff and how that impacts the ocean. And so here, for example, this is actually at a depth of 35 meters, showing in May a critical time for the marine ecosystem when the spring blooms are happening and that sort of thing, that there's going to continue to be the climate variability. This is just a single model run. And we don't know what, we can't trust the timing of the peaks and troughs in this temperature, but the nature of them, we probably have some confidence that it's reasonable. And it looks like, again, it kind of 2040, 2050, this particular run was with a little bit more aggressive increase in the CO2 concentration, which is looking more realistic than some of the results I showed earlier, for what it's worth. But anyway, it shows that by in the 2040s, we're going to be getting into very warm temperatures. What may matter more to the ecosystem, and this I think relates to the forests, a lot of the other components that we're concerned about is not necessarily the mean changes, but changes in seasonality. And here, what I've plotted, again, from just a single model run, so it's kind of tentative, and I just frankly didn't have a chance to look at all the ones that I'm in the process of looking at yet, is for the MLD, or mixed layer depth, right off the coast here, right off the mouth of Cross Sound. There's a seasonal cycle where the winds in the winter mix up the ocean, and then as it warms up, it shoals in the summer, and that shoaling is really key to the whole biology there. What this shows is that in the next couple of decades, the spring season is going to arrive maybe 2 weeks or even sooner than it does now. And a lot of that whole ecosystem there is critically, that's critical to it, the timing there. The zooplankton that eat the phytoplankton, they are expecting the phytoplankton to appear at a certain time, and if they're out there too early or too late, then it's not as productive, and it just, not as good for the whole food chain. So, one of the things that I've done as part of my work here, and again, this is in the spirit of kind of saying what our present capabilities are, and in particular the sort of things that I could bring to the table, is I've looked at the performance of these climate models in terms of their past these hindcast simulations and comparing them against observations. And there are some things, and these are just examples, and you'd come up with a different list of rationales if you're looking at the forest, let's say, versus the marine ecosystem. But there are some things they do well and some things they don't do as well. And in particular, just at the top there, point out that in the kind of large-scale wind patterns and ocean circulations and that sort of thing, it does pretty well. Some of the details, not as well. So just in closing, I want to, kind of reiterate that these simulations from the global climate models are being used to kind of anticipate climate change. I need some help from the folks like the biologists, the foresters, glaciologists about what sort of stuff counts, but perhaps I can help provide some of that information. At least for the next couple of decades, we have the luxury, in a way of speaking of, there's a lot of variability in the climate system. And so I think we don't, it's not like changes, point of no return, we're at there right away. That being said, we should continue to, to work on these things so that when we're just ahead of the game when these changes that right now seem inevitable do occur. And so just last couple thing is, I don't know whether it's this or that is going to be necessarily what it's like this summer, but I think we're going to be thinking it's more like this in a couple of decades from now. So thank you. And while Roman's gathering himself, if somebody has a question or, yeah, oh no, just stretching, okay. All right, thanks. Oh, hey, I got a customer.
Yeah, test. All right.
Just on. You can flip it back on again.
Test. Hello? Ah, forget it.
Yeah.
Yeah, I'm curious on the fresh water once it's coming out of the our coastal ecosystem here and it gets just offshore. And once those winds are starting to change, with that fresh water floating on top of the salt water, is that going to push the phytoplankton down below the photic zone so that the zooplankton have a harder time having a food source? And then also with that mistiming in the release of the salmon coming out, is that going to, I'm just wondering, how far are the salmon going to have to swim offshore to get away from the sweet water where the phytoplankton has access to the photic zone? And what do you see as the implications in regards to long-term stock assessments? Because if the juvenile salmon have to swim too far out and they don't have the energy reserves to be able to get that far or swim too deep.
Yeah, that's a great question. And about the kind of physics changes, I can maybe say something about that. I'll defer to my colleague Phil Mundy about what the implications for the assessment. But we do look at just this comparison in these temperature profiles, again, the kind of present climate versus the future. That it's temperature on the left, salinity on the right. It's not as dramatic there, but the freshening at the surface will kind of keep less dense water. It's going to be much less dense than it is now relative to the deeper water. So it's going to kind of, I would expect more intense but probably shorter lasting phytoplankton blooms, and conceivably less continued production over the course of the summer. And so I think that's the real concern there, that you'll have a brief bloom and then nothing to eat. But anyway, I better get on my horse here. Yeah. Any other questions?
So while we're switching over to my presentation, are we ready for a joke? Yeah? Okay. A short one. So there were these two hydrogens that were walking around. They were pals. And one turned to the other and said, "Hey, I think I lost my electron." And the other one said, "Are you sure?" And the first one said, "Yeah, I'm positive." Oh. Sorry. Okay. Okay, so what I'm focusing on is how the landscape has been changing in response to glacier changes. And just a little bit of a follow-up to what Nick discussed earlier. One of the drivers that we've now recognized in these large-scale changes we're seeing worldwide is the ocean. We recognize this in some studies we did over a decade ago, and now it's been shown and been implicated in destabilizing a lot of the major outlet glaciers in Greenland. So it's not only atmosphere, it's the ocean, and perhaps as I go into this talk, we can pick out some examples where this is going on. So let's see if I can figure this out. Here we go. So as a background and a bit of a template for where we're going, I chose this slide, which is just one group's rendition of what the last glacial maximum looked like in southeast Alaska. This was done by folks at NSTAR with contributions from many. I think it's still very debatable exactly what the late glacial maximum looked like in southeast Alaska. There may have been much more refugia than shown in this particular graphic. Nevertheless, there was multiple glaciations that swept across southeast Alaska, scraping the terrain, giving us a blank slate to rebuild on. And the last glacial maximum occurred here and elsewhere in the world sometime. The peak of it occurred around 16,000 to 20,000 years ago. Here in Juneau, it became ice-free about 12,000 years ago. There were some re-advances and oscillations, but basically we were ice-free in southeast Alaska in the fjord systems about 12,000 years ago. And what this implication for this is, there's an ongoing debate is how the first peoples migrated into the southeast Alaska. Obviously, this was not necessarily habitable during the period of the last glacial maximum, but once the glaciers withdrew, then you had land available for colonization. So ongoing debate, did the colonization occur via the ice-free corridor in the interior, or did the migration come down along coastal Alaska? And that's still ongoing. But what I'm mostly going to talk about is what's going on today. And there's looking at changing landscapes throughout southeast Alaska and elsewhere in the world for that matter. And we look at three different aspects: glacier, ice loss, and retreat, how that's changing the landscapes. And interconnected with that is how that's driving glacial isostatic rebound locally, and then globally, what we call connect globally, is how that's affecting global sea level rise. And if we have time, there are a few glaciers here in southeast Alaska that are actually advancing and how that's changing the landscapes, perhaps in some cases in a major way. So this is a pictorial, very local for those of you who live in Juneau or have visited Juneau often. You might recognize what we're looking at. The photo on the top is from 1893. 1893 from Ogilvie, one of the original, I believe, is USGS scientists who came in here to look at the Juneau mining district. And we're looking out towards the airport. You can see the little Ice Age tree line and moraine quite distinctly in the 1893 photo. And this is looking from Mount McGuinness outward. The bottom photo is by Craig Lynn, who occupied just about the same spot and what it looks like now. In the side there, you can see Jordan Creek, which by 2005 is pretty well hidden. It's pretty much dried up because it's no longer being fed by the glaciers. You also see Mendenhall Lake now is well formed by this period. So those are kinds of landscape changes we're seeing with the recession of glaciers. So we look at we've been looking at 3 different time periods, and not just myself, a whole raft of colleagues, both at the local university and my parent organization, which is the Geophysical Institute up in Fairbanks. We've focused on the Little Ice Age because that's when everything started for us here, kind of set the clock for current landscape changes we're seeing. We do that by looking at trim lines and moraines to try to establish where the glaciers were during the Little Ice Age and how far they've receded since then. We'll give you a type example where we've spent a lot of time looking at this, and that's Glacier Bay. The other aspect we looked at is comparing digital elevation models, essentially maps to other kinds of digital elevation models, and then comparing them to see how much ice has been lost between the two digital elevation models. And then the third part that we've been using and utilizing for the last 15 years, and it's accelerated in the past few years, is using airborne laser profiling and now LiDAR. And we have, I think, upwards at least 100 glaciers now under surveillance. We do it on an annual to biannual basis. So Little Ice Age, globally, most people put it around 1300 AD. It's probably a good time, start time here in southeast Alaska. We saw a sort of a synchronous retreat occur in southeast Alaska starting around 750 to the latter part of the 18th century. And the waning stages continued in some places all the way up into the beginning of the 20th century. This is Glacier Bay. Many of you probably visited it, and Kirk talked about it earlier about flying over it and being impressed by how much ice was lost in there. The advance occurred all the way out into icy straits. The final push apparently happened fairly rapidly. This was documented by some radiocarbon dating done by Kathy Connor and her group. And during this advance, there's a Tlingit oral history that describes villages that existed there around Gustavus area and at the mouth of Glacier Bay. And they talk about their ancestral hunting grounds in Glacier Bay. As the glacier advanced, it essentially overran the villages and pushed them out, and they had to relocate over to Hoonah. By the mid-18th century, the retreat started for whatever reasons, and by 1794 is when Vancouver expedition first came in there, and that's the mark we see on the map there. This is probably one of the, this to me is the largest non-polar collapse of an ice field that we've witnessed in modern times or since the Little Ice Age worldwide. It retreated 115 kilometers in about, what did I have here? In about 165 years, almost about 0.7 kilometers per year average over this time period. Now, this was not all driven by climate change. And this is one of the factors that we're deeply involved in trying to understand. It's most of this particular recession was driven by calving and this connection with the ocean. It was a glacier ocean instability in the deep fjords that caused calving, and it became a feedback mechanism of drawing down the parent ice field, thinning the glacier more, increasing calving, and so on. So it drove this process all the way back up into the bay. So we were interested for a variety of reasons, in part to look at what might be driving the rebound rates that we've seen around this particular region. So we reconstructed what that, we tried to reconstruct what that ice sheet, ice field looked like in the past during this little ice age maximum. And what we use, and this is also illustrates what happens when a glacier advances. When a glacier advances, this trim, we call this a trim line, where there's a demarcation between the forest above and fairly barren vegetation underneath. Above that is called a Krumholz forest. It's mountain hemlock that actually was alive, was not taken out by the advance during the Little Ice Age. Some of these trees are 700 to 800 years old, so they existed all through the Little Ice Age. But as the ice advanced, it actually sheared off all the vegetation, wiped the slate clean as it advanced out all the way into icy straits. But if we know the altitude of that and the position of that, we can use that plus many other markers, as illustrated by all the boxes here, moraines and nunataks and so on, to get an idea of just how big that ice field was on Glacier Bay during its maximum. And this is what it looked like. We put this together. And at its full maximum, it covered an area about 7,500 square kilometers. By 1948, this is what it looked like, a vast change. And that represents about 3,500 cubic kilometers of ice loss. And that's been going on. This is a comparison of digital elevation models we did from 1948 photography. That's what all the USGS maps were composed from. And then the Space Shuttle thematic mapper, radar mapper from 2000. When we difference these two, everything in red and yellow is ice loss. And you can see where the really bright red spots are. That's where the ice loss is the most. So what it illustrates is the continued ice loss throughout the whole Glacier Bay region, but also up further north there in the Yucatan ice field. If we combine these two, just to give you some idea what this represents, the combined ice that was locked up and then released into the ocean represents the entire freshwater content of Lake Huron, or equivalent to about 1 centimeter of global sea level rise. That's how much was involved in that episode, Little Ice Age episode. And just to show you what sort of landscape changes occurred, this is what it looked like in 2000 from the shuttle mission, looking to the west arm. On the west arm would be to that side, and the east arm, Muir Glacier, to the other side there. So we're looking up to where the cruise ships go up there to the Marjorie and John Hopkins area, and to the right to the Muir Glacier. This is a photo taken, I think, in 1894, and if you see the star and the arrow, that's where they're looking. So completely devoid of ice now. Muir Glacier is actually retreated all the way onto land, but just a little over 100 years ago, that glacier was way out to where these gentlemen are looking. And it's not, this ice loss is not restricted to Glacier Bay. It's been happening at all the major ice fields here in southeast Alaska, including our neighbor here, the Juneau ice field. Everything in red, again, and yellow is thinning. Stikine ice field, south of us, is also seeing quite a bit of ice loss. What's interesting is that where we see the most thinning and the most ice loss is where we observe glacier calving, either into a lake or into tidewater situations. You'll see one patch of blue here, that's Taku Glacier. If we have time, I'll try to get into what's going on there. The reductions in the Stikine ice field are mainly at the Dawes and Sawyer Glacier and LeConte Glacier. So just locally, again, looking at the change in the Mendenhall Glacier from the Little Ice Age. Those of you who are familiar with Juneau realize that the back loop road actually goes across a series of moraines that 250 years ago were covered by ice. You can see the location of the visitor center. Ice was there in about 1940 to 1950, and the red line shows you its present location. I think it's a retreat of close to 7 kilometers over that time period. Just to show you the landscape changes over this period of time, this is a bit of sleuthing or detective work by Richard Carstensen and his group. The upper photo is, again, from, I believe, Ogilvie from, this one's 1894. It's looking right up Mendenhall Glacier, and you're seeing the remnants of the Little Ice Age lobe streaming towards us, and in the background you can see Mount Bullard and then Taku Towers. The bottom one is from that very same spot. They've actually found the boulders where those arrows are pointed in the forest that exists there now, and this is what that area looks like. So it's been totally reforested and revegetated over this time period. This is what we're continuing to do now. Just some photos of the types of aircraft we've been using for LiDAR and laser profiling. And just to show that the ice losses within Glacier Bay are ongoing. Again, the red and the yellow show continuing thinning of ice throughout Glacier Bay. And this is a program that's we've been conducting over the past decade or more, and propose to continue for the next several years to monitor what the changes are in Alaska. So some summary conclusions. If I can read my writing here. The collapse of the Glacier Bay ice field is the largest non-polar post-Little Ice Age deglaciation that's known to us. All the major ice fields in southeast Alaska continue to experience ice loss and retreat. And this change, all these retreats and ice loss, has generated new landscapes, including all these deep fjords, proglacial lakes, and freshly exposed land, which is now available for colonization by plants and animals. The drivers of these include, which I don't have time to really go into, but it's the warming climate, the warming ocean, but the big question right now we're trying to understand and model better is the dynamic instabilities. Once these glaciers become unstable in a lake calving situation or a tidewater situation, how's that continued to be driven? So why do we even care about all this? Global sea level rise. Alaska glaciers contribute, up to just recently, Alaska glaciers contribute the most to global sea level rise of any of the major ice areas on the face of the earth. Greenland is now, I believe, taken over on that respect. But you can see the acceleration in sea level rise up to 3 millimeters per year. And these are the projections from IPCC and from others. Some projections up to 2 meters by the end of this particular century, more likely maybe a meter. And why is that important? Well, certainly if you're in a low-lying area, that's important because you have to mitigate it. You have to deal with coastal engineering of whatever facilities you're putting on the coast. If you're in the Navy, all your facilities are right along the coast, so you're going to be worried about it, sea level rise. And if you live in a low-lying country or have low-lying property, this is going to be a problem over the next several decades. So you don't need much sea level rise to impact a shallow sloped region. This just shows you the kind of effects that it can have say in coastal Florida or even Louisiana or Bangladesh. But here we have this regional effect. When we had the advance of glaciers during the Little Ice Age, particularly in Glacier Bay, it loaded the crust and actually depressed it, pushed it down, okay? So we actually had subsidence locally. And once all this ice is all melted out and it's continuing to melt out, you release that weight and it's like, in some degree, like a spring, it pops back up. But there's a second effect. The stuff underneath that spring is viscoelastic. It's like molasses, and it takes a lot longer time to re-equilibrate. So there's a lag effect in addition to the instantaneous effect. So what we're witnessing right now is a glacial isostatic rebound, basically due to the loss of ice during the Little Ice Age. Let's see if I can illustrate this here. The top model looks at a glacier advance. When the glacier accumulates ice, it increases the mass on the Earth's crust, so there's going to be local subsidence along the shoreline. And that's illustrated here. So when you have local subsidence, you actually have the ocean level rising along the shoreline, okay? But there's a secondary effect that ice has mass, part of the gravity. It's actually pulling the ocean towards you, so it's a double effect. Is that ice? So locally, we have the ice, we have the shoreline actually rising along the coasts here, but globally, sea level is dropping. The reverse effect takes place when you lose mass from the glacier. You start having uplift. When you have uplift, the actual sea level locally, and relatively speaking, is dropping. So locally, we have a dropping sea level, relatively speaking. We're both losing the gravitational pull, but also we have the uplift of the crust. So globally, with sea levels rising, but this paradox locally, we have land emergence. And here in Juneau area, it's about 1.3 centimeters per year. In Gustavus, it's about close to 3 meters, which we'll show you here locally soon. We've had a major program trying to measure just exactly what all this what the rates of this isostatic uplift is. And we use precision GPS techniques. This is in Glacier Bay. And just showing you the result of this, just focus on the bullseyes here. There's two right over Glacier Bay. One is at the head of the west arm, the other is at the head of the east arm. That's the Mirror Glacier and the Marjorie and Grand Pacific glaciers. And then you see another bullseye, that's the Yucatan ice field. Those rates are about 3.2 centimeters per year. These are the highest uplift rates we recognize on the Earth right now. But when did this all start? Okay, so I'm telling you it started with the Little Ice Age, and the reason we know that is because of a series of other experiments we conducted. We went around, so the top one shows you the effects of 1 minute. Okay, I'm out of here. I'll never get through. Okay, so we talked about global sea level rise, but the relative sea level rise is illustrated in the bottom graphic over here. If you have a chance to walk out to North Douglas, this is a perfect spot to illustrate that. As you walk down the stairs, you're actually walking down onto the Little Ice Age beach. Right at the bottom of that riser depicted here, you'll find that the trees, wherever we go, invariably are younger than 1750 AD. We just do tree coring, and you'll find that there's a progression of younger trees as you approach the coast. So we can use that. We can find actually the old beach line and measure the difference in sea level between the two. This is Admiralty Cove, a photo taken by Richard Carstensen, but it shows you exactly this effect. The young trees right along the edge are fresh colonizers of the recently uplifted land. As you go further inland there, you get older and older trees until you get into the old growth forest. So this is the result of all that. In Gustavus, we found that upwards of almost 6 meters of uplift has occurred over the last 250 years, and locally here in Juneau, it's been about 3 meters. And how that manifests is that in Gustavus, if you're familiar with the golf course, all that is emerged land, emerged tidelands, which has now been claimed as an accretion upwards of 50 acres. And I know Nature Conservancy has been working with putting a lot of the other land that's being uplifted into conservation units. And locally here, this has also affected the Mendenhall Refuge. Same kind of thing. The local seal trust has been working with people here to put the accreted land into conservation. So summary, just to summarize isostatic rebound, most glaciers are melting and retreating locally and worldwide. Sea level is rising globally at the rate of about over 3 millimeters per year, and it's going to increase throughout this century. Regionally, the rebound is causing significant uplift at rates of 10 to 30 millimeters per year. And this most prominent display of this is the emergent shorelines where we have shallow sloped estuarian environments. Young forests are now colonizing these uplifted beaches. And uplift will continue for several more centuries because of this lag effect underneath the crust. But if sea level continues to rise in certain regions, it's going to mitigate the coastal emergence and might catch up to the coastal emergence. So I'm not going to talk about glacier advance. If we have time later during the Q&A, we can talk about the effects of glacier advance in a couple of regions. And I'll just end it there. And say thank you.
Can't talk and set this up at the same time, I guess. Slideshow. So I'm Paul Hennon, forest pathologist with the PNW station. And today what I'd like to do is, for about 20 minutes, is give a little bit more, sort of hopefully kind of an optimistic talk about forests here in Southeast Alaska and north coast of British Columbia. And so when I entered the forest like you see on the scene here, to me it just feels primordial. And I think these forests gives the sense that they are timeless and they just don't change. And we know from discussions we've heard this morning and from our own knowledge that that's not the case. They've continually been altered by climate, and they always have been, always will be. But that's not the sense you get from them as you walk through them. They seem kind of timeless. Got a little echo here, but so what I'd like to do today is talk about some approaches that we use to understand climate change in forests, and I'll introduce, if you haven't heard of this topic before, I'll talk about bioclimate envelopes, or I'll just call them envelopes or climate profiles. And this is one of the ways that this is a tool that we use to understand forests and climate change, and can even be used for adaptation measures. I'll be well outside of my comfort zone in many ways. This is not really my topic of research. I'm a pathologist and I work on tree diseases and cedar ecology, so this is sort of stretching new material for me. But I can read the literature, so, and the literature is full of climate envelope research in the last 5 or 10 years or so. And so just really briefly, I'll describe what these climate envelopes are. When you see a map like you see on, I guess it's your right, this is a climate envelope of Douglas fir, from really one of the classic papers on this topic by Hammond and Wang from British Columbia, 2006 ecology. You see a map like that, that's an area of projected habitat where Douglas fir could grow. And to get to that sort of favorable climate zone for Douglas fir, you need to start with a good map of where the tree is, a species distribution map, train the climate information on that using some new really fantastic tools, GIS, where it's sort of GIS collides with climate, program like PRISM. Those use weather station data inputs, but it's possible to use some of the general circulation models that we heard Nick talk about and apply these to these models and then project these maps into the future. And when you do that, you sometimes see these expanses of great expanses in some cases of new habitat. Unfortunately, here in Southeast Alaska, for coastal Alaska, we don't have those published models for those climate envelopes. So what I'm showing here is just the full distribution of Sitka spruce, which covers almost the entire coastal temperate rainforest, the Pacific coast. And with a shifting climate, when we do have these models, and I think Dominic de la Salle is working on these models, and in the next few years, I'm sure there will be models emerging like this. We can look at we can look in different areas of the range of Sitka spruce, and what I would expect to see is stress in the southern part of the region, where we might look for drought stress, especially, maybe some insects and diseases related to that. And then in the north zone, this is usually an area of expanded habitat. We might look for tree migration. So in some sense, with these really simple approaches, and that's one of the points I like to make, is that these approaches are too simple in many cases, but we can use them to get some idea about how climates might affect our forests. And I think the lesson from these simple approaches is it really depends on where you look. And if you think about the tree species in coastal Alaska, Southeast Alaska, the north coast of BC, they have extensive ranges, and we're kind of on the northern end. And that's why I'm a bit more optimistic. These are places where the trees probably, not all of them, but probably many of them should be adapted to climate over the near term, certainly not the long term. This is a distribution map of yellow cedar, which occurs down into Washington and Oregon, and it shows the extent of the mortality problem, and I'll kind of end on that topic of the yellow cedar mortality problem. You can see that this does not occur just in the south end of the range. So it's one indication that these models, these approaches are a little bit too simple. Also, this idea of shifting climate zones it's a powerful concept, I think, and it gives us a good idea about how to frame our adaptive measures in terms of how to respond to climate change when we understand them well enough. But the main point I want to make is that the climate envelope approach is too simple. It's missing too much ecological detail, too much of the niche factors that are important to trees. For example, we need to know, with shifting climate zones, we need to know really how tree species migrate. So we need to incorporate those models and that understanding with things like dispersal, how do soils and disturbances affect tree migration and the way that trees are adapted to climate, inter-tree competition, and then biotic agents. I had to put that in since I'm a pathologist, insects and diseases. So what I'd like to do in the remaining minutes is use knowledge of our local tree species and use each of the tree species as an example to make a few of these points. And the first case with migration, I think is this interesting case, and I don't understand it very well, but it's the case of shore pine. And there's been a pollen study by Dorothy Petit, published several decades ago, and she found that shore pine, this has been known from other pollen studies, but shore pine has a distribution, the coastal variant of lodgepole, has a distribution along the coast up to Yakutat. And it looks like it appeared almost simultaneously about 10,000 years ago. It was the dominant tree here for about 1,000 years, but interestingly, it's shown no ability to migrate. So like, it looks like pretty much zero migration in 10,000 years. Interesting case, I think. When you're looking at the literature on dispersal, migration rates for tree species, it seems like it's hard to get ecologists to sort of answer that question, even though it's sort of a critical question. I think it's because it's a difficult thing to study, and more importantly, long-term rare dispersal events are probably really important in terms of dispersal species. But Petit and others have given some estimates, and when you change it from metric to English and multiply it by a century, their estimate of our coastal tree species is that they may migrate maybe up to 30 miles a century. So it's clear if these climate projections, where we're seeing great expansions in habitat in the north, if the migration rates are really only about 30 miles in a century, the climate is really outpacing the tree species, so we need to be aware of that. And we've heard a little bit about maps and how we're left out of, Southeast Alaska is left out of BC maps. I put in the distribution of western red cedar there, and this is a couple maps of western red cedar. So another example is Douglas fir. We don't have Douglas fir along the north coast of BC or in Southeast Alaska yet. However, the climate envelope work would suggest that in the future, Douglas fir might be well adapted to at least our climate here in Alaska. But it begs the question, how would it migrate here? And maybe its migration we might expect to occur in the interior where this is a fire-adapted species, but what about along the north coast of BC and in Southeast Alaska? Could it really make a living here without fire? So obviously disturbance is important consideration. And finally, the yellow cedar, that's like my last migration slide. The map you see on your right is our best yellow cedar distribution map of where it occurs right now. We have the strong suspicion that yellow cedar, unlike red cedar that migrated up the coast, yellow cedar occurred in these refugee areas during the Pleistocene. We show that on the map on the left. That's hypothetical at this point. We're testing this idea with a pretty aggressive genetic study, but we have the strong suspicion that yellow cedar migrated to the east and in fact is still migrating. If you've ever wondered why yellow cedar is so rare around Juneau, if we're right about this, it looks like it's just now arriving in the Juneau area. Key little, very small populations here and there around Juneau, even cases of individual trees. So it looks like it's just now arriving. And just to finish the yellow cedar, at least this kind of mapping part of it, it went on to die at the end of the Little Ice Age at a time when snow patterns were reduced, and this problem now covers about 500,000 acres. And I'll talk really briefly in a few minutes more about the yellow cedar problem, what we know about it, but the distribution of cedar decline that you see on the right has almost a perfect alignment with low snow areas. That was one of the first early clues that we got as to what was the cause of the decline problem. And the red areas that you see on the map on the left, this is a snow accumulation model by Dave Albert from TNC. You see almost this perfect alignment of yellow cedar with snow. So we can detect some widespread kind of in-your-face forest problems from the air and map them and sometimes understand them and in some cases understand that climate has a triggering effect of these things. But I'd like to talk about how we might get at more subtle changes in the forest, and that will almost certainly involve the use of inventory plots and monitoring plots. And that was a passion of our friend and colleague, the late John Coet. He was recovering inventory information and then analyzing it to see what it told us. And he helped us understand that the tree species here in Southeast Alaska have a strong alignment with elevation. We always had a sense of that in a qualitative way, but now we're starting to quantify it. So this is his plot data from one island, a bunch of stand exam plots showing yellow cedar dominated in kind of middle elevation and western red cedar low elevation. I'm not showing a couple species that have less tendency for elevation, like spruce and western hemlock. But we could take, the other thing we could do with some of this inventory data is the inventory plot data have dead trees as well as live trees. So we can plot the distribution of dead trees by elevation with live trees. And at least with this one species that's in flux, we can start to see just how the populations of cedar are changing. And it's sort of fading out of the low elevations. We know that snow, and I'll mention the cause of that, which is a freezing problem in a moment. We can see that it's holding its own at higher elevations. Yet other inventories, and this is a different inventory but the same latitude, have seedlings and saplings. And here, interestingly enough, we see yellow cedar, again, dying down low, holding its own in the middle, but regenerating quite well up high, higher elevation. So it kind of fits this idea of shifting climate zones. However, in this case, we're not talking about latitudinal shifts, we're talking about elevational shifts. And I think the key here is that analysis of inventory plots and probably especially long-term monitoring permanent plots is really the key way to get to some of these things. So now I want to switch gears and just show a couple of slides about the biotic factors. It's possible to have a tree species in part of its range favored by climate, where we don't expect it to be really having any serious problems. That might be the case for western hemlock at the northern end of its range. But what about some of the key disease and insect agents? And that one good example is hemlock dwarf mistletoe, which is also favored by the same climate conditions that are favoring some of the tree species. Less snow, longer growing seasons. We know something about the reproductive rate of dwarf mistletoe and what limits its distribution, both by latitude or by range, as I show here, as well as latitude. What we see here in the map is the range of western hemlock throughout coastal Alaska, and the tan areas are the areas that are also infected with hemlock dwarf mistletoe. So several hundred miles of disease-free forest with no mistletoe. Well, Tara Barrett from Anchorage has picked up on that idea and she did some climate modeling of both western hemlock and the pathogen, which is a parasitic plant, hemlock dwarf mistletoe. And she found it. I'll just kind of jump ahead to the lower right models. What we see here is, well, backing up to the first and the last models, is the green areas are plots that seem to have a favorable climate for western hemlock. The yellow overlaying dots are places that would have a favorable climate also for dwarf mistletoe. And so we see this great potential expansion of habitat for the pathogen dwarf mistletoe, but we know enough about the reproductive biology of that plant, which is dioecious, has boys and girls. Its migration is likely to be quite slow. So it's another example of altered habitat, but then really thinking about how quickly could a species really occupy that area. So the couple other sort of winners with climate, I think, would be Sitka spruce along the coast. But what about several of its insects? We have the case of the spruce needle aphid. It's favored by warmer winters, which are in the projections. This is an insect we want to keep an eye on. We expect it to increase its activity in the future. The same is true with a couple other actually more damaging insects. The spruce bark beetle is the same insect that devastated white and let spruce in the Kenai. It's here in Southeast Alaska, kind of eking out a living, but it's favored by warmer climate. So it speeds up its life cycle. Another insect, the spruce tipweevil, is not found in Southeast Alaska. It's found along the north coast of British Columbia. Very important forest management insect, deforms young growth spruce. And it's found just at the doorstep of Southeast Alaska. It's an insect we want to monitor for. We know that its range is limited by growing degrees in the days in the summer, something else that's projected to increase. So we want to monitor that insect. So I'll close with a couple slides of the yellow cedar decline and kind of what we're doing on that problem. I won't have time to really get into the details of what's causing cedar decline, although I'll just say that it's a freezing injury, the proximal injury. It's a freezing injury, and there's several site and stand and vulnerability issues related to cedar that kind of set it up for this problem. A key one is shallow roots. The trees are dying on wet soils, forces the roots to be shallow. And then another key element is snow. Snow is the environmental change that occurred. The cedar trees grew up, most of the mature trees grew up during the Little Ice Age, or some were even regenerated and grew up before that. But they're now dying, and you saw the effect of snow. So what we're doing now is we kind of took all that complexity that we think causes cedar decline, and we've focused on just two landscape features that we can model on the landscape, and that's snow, which is a dynamic factor that changes through time. So its behavior on the landscape will probably start to mimic the climate envelopes a little bit, kind of shift through time. And then the other variable is drainage, which is the other sort of key variable. I've been really brief with our cedar story. If you want to know more about it, come see me. We also have reprints of a new paper in bioscience. It's in the P&W booth in the next room over. So I've been a little bit too brief with this, but one of the points I wanted to make is we've found a way by kind of keying on these two landscape features, snow, and now I'm showing these ellipses as snow zones, so we've sort of focused on the mechanism of cedar decline, modeling snow zones. And then the drainage is a finer scale feature we've embedded in the snow zone, which is sort of broader zones. And I think for forest management, maybe what's interesting here is we found some habitat in the low snow zone that's favorable for yellow cedar, and this is on deeper, well-drained soils. So there's management space here, and this turns out to be the sort of productive areas of commercial forestry in the low snow zone for yellow cedar. And what we're really advocating here is a solution for this yellow cedar problem is to shift its ecological niche, kind of nudge it over into the well-drained area. And that's something we can do with forest management of thinning and planting. I also wanted to make a plug for a team that I'm on now, which is a U.S. Forest Service team. We're writing a comprehensive management strategy, conservation strategy for yellow cedar, kind of using this new science. And at its basis, we're partitioning the landscape into habitat that's suitable or unsuitable for cedar, as I talked about. And then we expect this document to have really all the details about the ecology and the silvics of cedar that help land managers consider sort of conservation and management activities with regard to cedar. So I don't know if I'm out of time, but I think the lessons from some of this work is that hopefully is that a bioclimate envelope is not the same as a climate vulnerability assessment. We really need a lot more detailed ecological knowledge to add to these climate envelopes to make them useful. In the future, we might expect surprises in different parts of the range for a tree, even a paradox, like with yellow cedar decline, a freezing problem in a warming climate probably seems paradoxical. Climate change, climate zones will probably shift faster than trees can migrate and respond to. And I think we need to infuse those climate envelopes with things like soils, disturbance, and these biotic agents. And it's clear to me that this will require the help of all sorts of disciplines. That this has to be a multidisciplinary solution, people working together. And we need, and we already have management experience with cedar, and that's going to be an important part of the future, as well as monitoring plots and sort of analysis like John Coet was doing. And finally, I just put that we'll need social acceptance of some of these adaptive measures. So I think education is obviously going to be an important part of this message too. So I don't know if I made 20 minutes or not, but I'll stop there. I don't know if we have, you want to do questions later, Tom, or?
One burning question. You can't wait a few more minutes? We'll go ahead and
good afternoon. It's a pleasure to be here with you today. I want to start by thanking Michael and the ACRC crew and the symposium staff here for being so good to me and making it possible for me to be here today. Also want to point out, if you looked in the program, that I am not the director of the Alaska Fisheries Science Center. I have to say that because the director of the Alaska Fisheries Science Center is my boss. I am the director of Auk Bay Laboratories as part of the Alaska Fisheries Science Center. We've got a booth next door, and I urge you to go over there and take a look at it. We operate 5 facilities here in Southeast Alaska and 2 out in the Pribilofs, and our headquarters is the Ted Stevens Marine Research Institute out at Lena Point. Okay? So, what I'm going to do for looking at climate drivers and coastal ecosystems is I'm going to round up the usual suspects and then talk about what we're actually measuring here in Southeast Alaska. A recurring theme here is that long-term monitoring is essential if we're going to understand climate change in coastal marine ecosystems. If we're asking if climate is going to change things, are coastal communities going to be advantaged or disadvantaged in Southeast Alaska by climate change, we have to have some sort of benchmarks against which to compare the things that we're seeing. So if you look at the climate drivers that are listed here, you're going to see this slide again a number of times, but we have inputs from the ocean, which are very important. Ocean carbon and nutrients come into coastal marine ecosystems and into the rainforest from the ocean. We have inputs from the rainforest into the coastal marine environment that also go into the ocean. Terrestrial freshwater, iron, very important, carbon and nutrients. And then thirdly, the seasonal distributions of heat and freshwater runoff interact with changing elevations, such as you've seen isostatic rebound may cause. The seasonal distributions, or the hydrograph of the freshwater, are particularly important. Then the last one there, this seasonal hydrograph in coastal environments is very important for determining the impact of ocean acidification. Ocean acidification is of course being caused by increase in carbon dioxide in the ocean as a result of the increase in the atmospheric levels. All right, so set the physical stage here. We can't forget that the Tongass sits on the edge of one of the world's deepest oceans. We sit on the edge of a giant tub of fertilizer. Deep ocean water is loaded with nutrients. When things die, they sink, and deep ocean water gets full of it. So here I've got an elevation map. You can see the coast of Alaska shown in gray there. The blues are shelf, 100 meter and 200 meter. And then if you go 40 miles off of Sitka to the west, you're pretty soon approaching 1,000 meters deep in water. And then in the green there toward the yellow, it's 3,000 meters, 4,000 meters. 4,000 meters is a lot of water. And over by the Aleutians, you see that bright red streak there, and that's 7,000 meters of water, one of the world's deepest points. All right, so here is a conceptual model of the coastal ecosystem here in Southeast Alaska. And kind to talk to you about a slide like this without a pointer is sort of like talking with my hands tied behind my back, but nonetheless, get oriented and look at the middle of the screen, and you see the yellow arrow there that says wind. This is what Nick Bond talked to you about earlier. You've got there the Alaska Current and then the Alaska Coastal Current. The Alaska Coastal Current is a what they call a buoyant boundary current, meaning that it's got fresh water in it and it's driven. Then look in the lower left there where you see it says Gulf of Alaska, but that's where the deep water is, and how that deep water sloshes up out of that huge tub out in the Gulf of Alaska into coastal environments makes a big difference, because these fertilizers, nitrogen-based nutrients, are not going to do much for biological productivity unless they can get into the sunlight. And so they've got to get above 100 meters in depth before they'll drive biological productivity. If we look at the circles that run along the coast there, this emphasizes the fact that people are part of the ecosystem. Human activities really do impact the way that climate change will be perceived and will act. And the coastal rainforest is part of the coastal marine ecosystem. The interaction there is sometimes very acute, but mostly very subtle. We don't often think of the coastal marine environment as part of the rainforest, but it most certainly is. So here we are back at that slide, and I'm going to talk a little bit about the inputs from the ocean here. So we know that ocean carbon boosts coastal food webs in the Gulf of Alaska. If you move to the north and look at Prince William Sound, where we had the oil spill in 1989, we've done 20 years of work up there, over 20 years of work, very intensively in Prince William Sound. Note that Prince William Sound is basically a very geographically compact version of southeast Alaska. It has lots of independent drainages that produce salmon, lots of fjords, and a very sharply demarked coastline without too many estuaries. This is a study by Tom Klein at Prince William Sound Science Center, and emphasizes the fact that when Prince William Sound is connected to the Gulf of Alaska, lots of good things to eat for the fish come pouring in through Hinchinbrook entrance, and you get a boost in production. Okay, now we'll move back to southeast Alaska, and we'll talk about the Southeast Coastal Monitoring project, which has been going on since 1997. This is a vessel-based survey where we tow a net through the water, catch small fish, tow a smaller net through the water, catch zooplankton, and then look at the physics. We measure temperature and salinity at depth. This will show you where where we go. Basically, the most important place for this survey is up at the choke point at Icy Straits, where we can find the juvenile salmon just before they go into the sea. We've learned recently that how far the Gulf of Alaska actually intrudes into southeast Alaska is really important because it may intrude quite a bit farther into Icy Strait than we had thought before. So what is all of this good for? These are forecasts and actual returns for pink salmon abundance in southeast Alaska. I started in salmon a long time ago. I know that pink salmon are very hard to forecast. We've used adults, we've used catch, we've used eggs in the gravel. Nothing works better than a moving average. Nothing works better than just sort of guessing at it. Nonetheless, here from 2004 to 2011, we didn't do too bad. In fact, there was only one time, 2006, when we missed. So you can't, the chances that our forecasting method is not dead on are very, very small. And what this says is that salmon year class strength is set in about the first 6 weeks of marine life. That what happens in fresh water is not very important for telling you about the adult abundance that are going to be hitting the fisheries when the fish mature and they come back. Not saying that freshwater work is not important. I don't want to get into any fights during the beer hour, but we find that looking at the marine environment is extremely important because that's where year class strength is set. And in fact, this shows you that in all years except for 2006, what happened after the fish left southeast waters and went out into the Gulf of Alaska also was not very important in terms of forecasting because the survival out there was about the same in all those years except for 2006. Looking at terrestrial, freshwater, iron, carbon, and nutrients, and what we've been able to measure. We have just started a thing called the Gulf of Alaska Integrated Ecosystem Research Program. This is a partnership with NOAA, North Pacific Research Board, University of Alaska Fairbanks, and 8 other partners. And we are looking at what's coming out of Southeast Alaska as well as what's going in. This is physics to fish. We're particularly interested in things like rockfish and sablefish in the course of this study. We we started this in 2010 with some preliminary surveys, and we expect to conclude this in 2014 with a year of analysis. But what I want to point out here, again, is that we have set up a large number of observations, the blue dots there on the right-hand side off of southeast Alaska. These stations will collect physical oceanography, nutrients, phytoplankton, zooplankton, and small fish abundance for this area. Looking at seasonal distributions of heat and freshwater runoff and how they interact with changing elevations. Well, I think we have already had a pretty good laboratory in Alaska for looking at the potential effects of isostatic rebound on salmon populations. In the 1964 earthquake, elevations changed in a lot of different parts of Alaska, but in Prince William Sound, in the outer area, they changed by over 64 feet up, and in the inner areas, I think they dropped by about 32 feet. The result was, and there's a nice National Research Council report from 1968 about all this, that streams were flooded, or streams were lifted up, so that the gradients were changed, and it was a disaster, particularly for pink salmon production in these short little drainages, the 820 of them around Prince William Sound. If you take a look at the red arrow there where it says earthquake 64, the wild populations were at relatively low levels, that is relative to what they are now, but they dropped down to very low levels after that. Now, what the long-term impacts of the earthquake would have been, I don't think it's easy to say from this, because we had during this time period between 1968 and 1977 in Alaska generally some very, very cold winters, and I'm speaking here not from data but from experience. And a lot of the smaller streams froze right to the bedrock for 4 or 5 winters in a row. That's not very good for salmon populations. And to the extent that the state of Alaska invested many tens of millions of dollars in the 1970s to get hatchery programs going. Now you see off here on the right-hand side that a good part of the production in Prince William Sound is now coming from hatcheries and not from wild sources. Lastly, here the seasonal distributions of heat and freshwater runoff, how they interact with changing elevations. I want to talk about Auk Creek Research Weir, which is about 13 miles outside of town here. This is a fence across the river where we count fish. The federal government used to operate hundreds of these in Alaska starting in the 1920s. I believe this is the only one operational in Southeast Alaska. It may be the only one operational in Alaska, at least for the federal government. State of Alaska still has a number of fish weirs. This is painstaking work where the fish are counted, the adults are counted into the stream and the young are counted out. It's a really good long-term signal on productivity in the freshwater environment. And what a long time series like this is good for is that you can use it to look at changes in phenology. Phenology is the study of the timing of the life cycle within the geographic reference frame of the species. Here and the question here is, well, has climate change changed anything biologically in Southeast Alaska? Has it changed anything physically that interacts with the biology? And the answer in both cases here is yes. You can see in the bottom panel there the average annual water temperature in Auk Creek has increased, a significant linear trend upwards. The date of ice out appears to be decreasing, but that trend has not been significant. Here we have looking at the average water temperature only during the time period of incubation, mostly during the winter when the eggs are in the gravel and the young hatch out and are growing. That's a very significant trend, very strong trend there. It's increasing from about 1963 to present. So what does this do? Well, it means that according to the solid graph there, that there's a trend of earlier and earlier emergence. That is, the fish are coming out earlier and they're going to sea earlier every year. Significant trend in that behavior. As we've heard earlier in the talks, the match between the emergence of the fry and the entry into marine water and the plankton bloom, the cycle of the plankton bloom is very important to their survival and to the future of the fisheries and the coastal communities on which depend on the fisheries. So the seasonal distribution of freshwater runoff will determine the impact of ocean acidification on coastal marine environments. The rising acidity or decreasing alkalinity of the marine environment as a result of increasing CO2 concentrations in the atmosphere means that anything that uses calcium carbonate in its body and that has to expend energy to get calcium carbonate into its body, such as crustaceans, copepods, some of the most common animals in the ocean, they'll have to work harder to get it. And if the bioenergetic requirements of getting that calcium carbonate into the shells that they make for their body exceeds the amount of food that they can get, then they don't survive. Here we've set up some stations along the Gulf of Alaska, including here in southeast Alaska, to look at ocean acidification. I'm going to talk just about the stations that are from the Auk Bay area, Favorite Channel, and up in Lena Cove. In looking at the levels of pH, which is the blue graph here in the left-hand panel, this is the Central Pacific Ocean. This is the Aloha line. And I've got a number. The orange is total alkalinity. The green is total dissolved inorganic carbon. These are all measures that are proportional to pH, depending on the circumstances. And that's the way it's supposed to work out in the ocean. You can see the pH scale is, can you see that cursor? Do you see the cursor on the screen? No? Okay, too bad. The pH scale's on the right-hand side, and in general, pH in the ocean out there runs in the high 7s and low 8s, and it doesn't change much. That's the point of the left-hand graph. On the right-hand side, there you see coastal water in southeast Alaska from our sampling stations, and it changes. It really jumps up and down seasonally. That's going from the September of 2009 to September of 2011 on the time scale there. And this is what's going on in the coastal environment. You've got a seasonal pattern of discharge, seasonal pattern of, therefore, of salinity. As the discharge goes down, the salinity goes up, and conversely, and a seasonal pattern of precipitation. Here, again, is the same sort of seasonal cycle, and it's with photoperiod in the red imposed on it. The point here being that pH already varies a lot, goes up and down a lot in coastal environments, and organisms in coastal ecosystems are therefore adapted to handle these sorts of changes. I think that coastal marine ecosystems are going to be much more resilient towards changes in increases in ocean acidity than you'll find in oceanic environments, which are relatively constant, and where the organisms are not adapted to dealing with changes in ocean acidification. So let me close by saying that the prognosis for Alaska's resource-dependent coastal communities, in terms of the changes in the resources on which they depend, seem to me to be relatively minor in the short term. And the caveat here is that I'm talking only about climate drivers of change. I'm not talking about things like sea otters, which are increasing and moving up from the south, and which will ultimately result in loss of things like Dungeness crab fisheries. We saw this in Prince William Sound 25 years ago it's coming to Southeast Alaska. I don't see that as a climate driver, but that is something that will interact with climate change. So the interaction between climate drivers and other things such as biological factors and human factors are things that need to be watched closely, and therefore we need long-term monitoring programs. We need eyes on the ocean and eyes on the plants and animals in order to understand climate change. Thank you.
All right, well, thanks everyone for sticking around. My name's Aaron Hood. I'm in the environmental science program here at UAS in Juneau. And I'd like to start by thanking our 4 speakers. I think they did an outstanding job of highlighting one of the really fundamental characteristics of this region, which is the tight coupling between terrestrial and marine ecosystems, and then looking at changes in the atmosphere and thinking about how those are going to impact ecosystems in terrestrial and marine sphere individually, but also impact the interactions between those. We have about, I think, 15 minutes left here, so I'd like to invite you to ask hopefully some hard and maybe cross-cutting questions that the panelists can try to tackle. All right, Kirk again.
Got me on okay? There? Yeah? I guess this is a follow-up on with Phil and Nick there on both of those. And you probably heard my question with him in regards to the changes in wind patterns and that freshwater lens that tends to push out and keep that the phytoplankton below its potential photic zone. I noticed on your one slide, with the change in the wind patterns, we may be getting, if it's a little bit more westerly, it looked like Northern California, Oregon, Washington, southern BC is going to get a lot more upwelling. And with those change in wind patterns, we may be getting more downwelling, which is going to decrease our nutrient availability for our phytoplankton and our zooplanktons. With that in mind, understanding how these wind patterns change, it sounds like that you're implying with our hatcheries, we can time the release of the hatcheries so that we know that there's, as you're mentioning, the inshore versus the offshore survivability isn't as important as the nearshore survivability of these salmon species. It sounds like, please correct me if I'm wrong, but it sounds like you're implying that some of our hatcheries can time the release to ensure the future higher productivity of these adult stages. With that in mind, and you're saying the resiliency of our natural stocks that live within a changing variability is a lot higher in our nearshore species versus species that live in the middle of the Pacific Ocean. What type do you see, since these our natural run of fish don't have that ability to go, hey, I think we'll just hold off until that freshwater lens that allows us the availability to get to the zooplankton. Do you foresee the resiliency of our natural run species to be able to adapt to these rapid changes? Are they showing the ability to adapt to these changes? And if you could, and I appreciate the crossover between the wind and the currents and the upwelling and the downwelling. Thank you.
Okay, yeah. With regards to the winds, I'm not sure how clear I was, but they're the kind of the variations from year to year and decade to decade are going to dominate any sort of systematic changes in the patterns, at least in the foreseeable future. And so you're exactly right, though, that it looks like there might be a little bit more upwelling to the south of us. Actually, in the summer months, maybe a little bit more in these waters also. But at least our best climate models aren't showing big changes in the mean pressure patterns and winds. I should add, though, there's the potential for probably more extreme events, and a lot of you may have heard about this just with the kind of juiced up atmosphere, higher humidity, more, not necessarily more storms, but the very strongest ones even stronger. And so the implications for that, for the forest and the ecosystem, I don't know. But I'd say the wind changes aren't right now first and foremost on my mind.
Yeah, well, there's about half a dozen questions there, so maybe I'll just cherry pick a couple that I want to answer. But first of all, remember that model conditions are in essence averages, and when we're looking at when we're trying to match biology to physical models, we sometimes get a mismatch between time and space scales. So we get down. Biologists always want finer and finer time and space scales, and the data which is available to the modelers doesn't always permit us to get to finer and finer spatial scales on there. When you're dealing with salmon entering, leaving freshwater and heading into marine water, you've got a relatively small window there. So while the IPCC projections can tell you what the average conditions are going to do, and then on the average, you may get more downwelling. What really matters to your class strength in most salmon populations in Alaska is what happens within the first 6 weeks after they hit the salt water. So even though average conditions may be more downwelling, if you happen to get a set of circumstances that produces upwelling during that time, well then everything is good. Secondly, here in Southeast Alaska, we're still learning a lot about the physical oceanography of the near-shore shelf area. I heard one of Nick's colleagues speaking here in Juneau about 3 weeks ago say that the Alaska coastal current is discontinuous in Southeast Alaska. Now that kind of knocked me back on my pins. Because I'm still trying to figure out exactly what that means, but she was speaking about the situation in Lower Chatham and in Cross Sound. And that was a comment that I made during my talk about how far does the Gulf of Alaska actually extend into the waters of Southeast Alaska, the coastal waters. That's a big deal. That makes a very big difference for the reasons that you have mentioned about the depth of the phytoplankton and the fish finding food, among other factors. And then I just quick wanted to say about the hatchery releases and timing the hatchery releases and so forth. That was not my point in bringing that up. We have in Prince William Sound Aquaculture Association has samples for zooplankton and tries to release their fish in synchrony with the blooms. I think that, but there is also, depending on the species, a limited window of time that they have to play with in terms of synchronizing their releases to the phytoplankton bloom, and they're going to have to let them go sooner or later, whether it blooms or not. So.
I thought I'd say something about wind, but we probably won't get any forest questions, so I'm going to jump on the wind, and I know Paul Alabac there is probably thinking about wind here. Well, as Paul talked about earlier, wind is like the key disturbance agent in our coastal forests, and we have wind events every so often that causes partial disturbance of the forests, and every once in a while we have really big wind events that are catastrophic and in some ways dwarf the activity of, say, timber harvesting. So we had an event we think it was 1883 or the 1880s, that knocked down tremendous areas of forest. There's a number of areas around all over Southeast Alaska that are kind of date back to that age. So that's kind of one point. And the other is, I believe that wind is not included in most of the climate envelope work that I was talking about. It could be, but it's not. And it could be very important in a place like Kodiak, that spruce is migrating sort of across a fog neck in Kodiak Island, and the temperature and precip values might be perfectly suitable for Sitka spruce to migrate down the Aleutian Islands, but it might not be very happy about the chronic wind patterns that occur there. So I think we do need to think about wind with regard to the forest.
Thanks very much for all the presentations. Many of us who live in Southeast Alaska, of course, live really close to the high tide line. And I heard today that the sea level rise is about 3 millimeters average per year. I was just wondering how long it's been at that. When can we expect, or when are we guessing that it's going to increase? And so I guess when are we going to hit a place where people actually start to feel impacts from sea level rise?
Depends where you live. The distribution of isostatic rebound peaks in Glacier Bay, and it falls off almost radially away from Glacier Bay. Locally, we're experiencing about 13 millimeters of land emergence per year. Sea level rise right now is currently at a rate of about a little over 3 millimeters per year. And that's the acceleration occurred over the last decade or so. And the projections are, a best guess, maybe, it's really hard to project all the way out to 2001, but the best 2100, with the best projections maybe put at about a meter sea level rise over that time if everything continues on the track it's going right now. So what is that? That's about, that'd be about 10 millimeters per year sea level rise. So we, here locally, will continue to outpace sea level rise. But if you go to Sitka, where it's about 5 millimeters per year, then it's going to reverse. Someplace in there, someplace during this century, you're going to have sea level rising there rather than the sea level dropping, relatively speaking. I don't know if that answers your question or not. Okay.
Oh, yeah.
Yeah, I serve on the board of the Spalding Beach Condo Association out at Auk Bay, and one of the things that we've been debating now for the last couple of years is whether to go ahead and spend the money to lay claim to the land that's emerged out there, because there is a slim possibility that somebody could jump our claim, but there's enough land that's popped out around Auk Bay that people are starting to, wondering whether they need to go down and improve it up and file a claim on it. So I think we are seeing that at the tide line here in Southeast.
Other questions?
Hi, thank you to all the presenters. I enjoyed that. I didn't get the sense from anybody that there are going to be dramatic changes due to climate in the near future in Southeast Alaska, and I'm just wondering if I missed anything, first of all. And second of all, it seemed like one of the major changes we can expect would be due to glacial retreat, which does not seem to be linked to climate directly. And I was wondering if, Roman, you could expand on that.
Yes, I did try to give that impression that, again, the kind of variability in the climate will dominate the trends in the short term, by that meaning a decade or two. But in terms of we are already starting to see some changes there. And the changes, maybe not as much in the winds and so forth, but in the warming temperatures and the changing of the seasons of the hydrography. I think that is happening, and that is liable to continue to happen. And so in terms of just how fast the glaciers are going to change, that's not my area of expertise. But I did give the right impression then that we shouldn't be alarmed right now, but this means there's an opportunity. And in case there's some time after there's some questions, I have a modest proposal. And so just for the others, I'm just going to, if we have time, I'd like to talk about that. But Roman, yeah.
Two-pronged answer. The general trend climatically has been for increasing temperatures locally. I think we've increased about 1 degree centigrade over the past 50 years, and it's echoed in Sitka and Yakutat. So just sheerly by warming trends, we'll probably see continued wastage of glaciers, and that's been the trend we've seen for the last several decades, if not centuries. The other part of this is the dynamic effect, which we're keep trying to understand better. Coupled with the atmospheric warming is also ocean warming. There's buoy that's been maintained by the University of Alaska Fairbanks, IMS, or now School of Fisheries, Ocean Science, that's spans at least 3 or 4 decades of data, and the buoy samples temperatures all the way down, I believe it's 280 meters. And it's right in the Alaska coastal current, but it's at the kind of the Prince William Sound end of it, okay, before it starts going up into the Bering Sea. The long-term record was extended by some ship observations. This is by Tom Ryer. Anyway, the general trend is at all levels, the ocean's been warming, and it's been becoming fresher. So the reason I bring that up is because we've seen this coupling between not only the atmosphere with glaciers, but also the ocean warming with glaciers that enter into the ocean. We're witnessing disintegration right now of one of the major tidewater glaciers up near Valdez. That's the Columbia Glacier, and it's continuing to go. Here locally, we have seen this effect in Glacier Bay, where dynamics really drove that retreat. Recently, we saw it not far from here in Tracy Arm, where the South Sawyer Glacier retreated 2 kilometers in less than just about a 2-year period. It's restabilized, but it'll continue thinning, and as it thins, it'll probably again undergo a calving retreat. So that's the part that's a little harder to model. We can probably, and that's something that actually Eran and colleagues at University of Alaska Fairbanks are working on, looking at what a warming climate will do, just that part of it, how it will affect glaciers over the long run. That's easier to model. It's not easy, but it's easier to model than trying to understand what the dynamic effects are doing. This is a contrast in Greenland, which is now the big elephant in the room. Antarctica is next. 50% of the ice loss out of Greenland comes from dynamic effects. It's the glacier calving and the thinning associated with it. If you go up in the Chugach Mountains, Columbia Glacier and associated calving glaciers there account for 50% of the ice loss coming out of those mountains. I don't think we've evaluated yet for the Stikine ice field. So the general trend is that we're going to continue to see ice loss locally and worldwide. If that answers your question.
I wanted to say something about the forest, because I think a key part of our climate is that our wintertime, average wintertime temperatures at most weather stations are close to sea level. And through mild warming, I think a key thing to understand with our local climate is that we could have a mild amount of warming, but we're passing this threshold of rain and snow. And so it doesn't take very much warming to do that. And I think evidence of that is what's happened to the cedars. So that's a pretty dramatic effect in the landscape, 500,000 acres of dead cedar and more down in British Columbia. So I think anything that, any ecosystem factor that we can think of that is somehow tied to snow, we need to be concerned about it and be thinking about that.
So I have a couple questions that tie into that, and one is I didn't hear anybody talk about the effect of albedo as we lose glaciers, and this is really long scale, but that there's going to be a difference in reflectance, and also the fact that we're losing that ice mass and how that affects temperature and climate, and will that change? Has anybody taken that into account in any of the modeling, that may accelerate at some point how the warming progresses? And my original question before I thought of that was, are there any key areas that you would say from your different disciplines are particularly vulnerable in the next couple decades?
I'll just offer a partial answer. The albedo is important. It's important locally as our glaciers retreat. We have a lot of microclimates. Anybody who lives in the Mendenhall Valley realizes this is usually 5 degrees cooler there. So if we lose our glaciers, lots of changes will occur. You'll no longer have that stream of meltwater coming in the summer. So that's going to change the basin ecology. Without the ice there, you may not have the microclimate effect that you witness now. Losing ice off the surface of the earth will increase the absorption of sun, and I suspect it's probably included in all the climate models. But the big factor is the sea ice. in Arctic. We're losing it at a prodigious rate. And now you're exposing where we used to have all this being reflected across the Arctic Ocean, that's not being absorbed by the ocean. So that's a big major change, and of course a lot of people are looking towards that. I don't think it's been this year. I think this year was the second greatest retraction of the sea ice pack that we've seen since records have been kept.
That's exactly right. 2007 was the record melt back in the summertime. It turns out the area covered by the glaciers here is relatively small compared to, of course, the area of the globe itself. And so globally, it doesn't make as much difference as Roman mentioned, as the Arctic and Antarctic regions. I'd like to address one of the questions about the kind of sentinels for climate change. And they're kind of from the kind of marine ecosystem perspective. I think just knowing how the top part of the ocean monitoring not just the sea surface temperatures, but the upper ocean profiles of temperature and salinity, being able to keep track of it as these glaciers melt and maybe the fresh water is getting out there sooner or at a different time of year. That's something that is well worth monitoring in a better way than we do it now, because it's not easy to take subsurface ocean measurements.
I want to say something about the vegetation here, especially the bogs, in terms of vulnerable systems we might be concerned about. I think our bogs and peatlands would be some of the plant communities that we want to keep an eye on, especially since their carbon sinks or have been in the past, and with longer growing seasons, warmer temperatures, we're somewhat concerned about greater decomposition rates and release of that carbon, as well as just the plant communities that exist on that sort of continuum to bog to forest to wetland to upland forest.
I think we have time for one more question here.
I'm Rick Caulfield, Provost at the University of Alaska Southeast. Thanks for your presentations. And I just wanted to ask, the Alaska Coastal Rainforest Center has as a goal increasing interdisciplinary collaboration on research and also expanding the public's awareness about ecological dynamics in coastal temperate rainforests. As you think ahead over the next 5 to 10 years, where do you see the greatest opportunities for increasing collaborative research? Where are the gaps that we can really focus on through an organization like the Alaska Coastal Rainforest Center? Thanks.
Yeah, thanks for pitching me the meatball there, Rick. Yeah, obviously the freshwater inputs to the marine environment are extremely important, not only in the coastal ecosystem, but in the near shore, as the Gulf of Alaska, which Nick addressed earlier. We, as an agency that's focused on the marine environment, at least in the last couple of decades, we've been focused on the marine environment. We definitely need partners who can help us with that terrestrial marine interface. We need, and getting across agency boundaries is not that easy. I mean, we do it one-on-one, we do it scientist to scientist. But if we spot the need for an additional program that has additional cost with it, well, that then quickly becomes an institutional matter. And I think the ACRC has been very valuable just in allowing me to talk to groups of scientists and to types of scientists that I don't ordinarily get to interact with here in the Juneau area. So I think it's a terrestrial marine interface and how we bridge the data gaps across that, get the appropriate input for the marine environment, and also allow us to provide the appropriate inputs from the marine environment to the freshwater scientists.
Yeah, if I could also address your suggestion, and there, I think potentially a role for ACRC would be to help to kind of galvanize that kind of interdisciplinary work, would be to kind of set up, and this was my modest proposal, and forgive me for bringing it up, but a kind of a experimental seasonal forecast system. Tom Ainsworth and company, the National Weather Service runs climate models for seasonal weather prediction. We can use those models to, right now, they're available out 9 months to a year, to kind of anticipate what the climate's going to be for the next year. And I suggest that we would learn how these different pieces work together by trying to make forecasts. And we don't have to wait for the climate change in 20 years. We can see whatever the climate delivers for the next year and see if what we can anticipate and what we can't. And so my modest proposal, if the ACRC was able to organize a workshop getting together people who would just basically, maybe it'd be at the level of conceptual models or maybe some very relatively simple dynamical models, using that term very loosely, that'd be put into it, but start making forecasts and see what we need, what we don't understand, what we can actually forecast, and what we need to monitor better so that we could potentially do it. So that's my suggestion. It turns out we're actually doing that on the, along the Pacific coast, a program just starting up. And so I don't have the results there, but I think it could work here too.
Okay, any other comments, last comments here? Quick question.
Sorry, I was kind of waiting in a chair and not stepping forward earlier. But so Paul and I worked together, and we've talked a little bit about climate envelope models, and he expanded on that in his talk about what some of those models are missing. And so, you know, these are models that look at thresholds for different tree species and where they might do well in future climate scenarios. And so there's a lot of interest in the western United States in, you know, predicting where species are going to do well and then moving them either to higher elevations or northward. And it sounds like most of our species in Southeast Alaska are going to do okay, at least in the near-term climate scenarios. But Paul, what do you think about the interest in bringing other more southerly species like Douglas fir that we really don't know how well they're going to do here? What are some things that, other than filling some of those knowledge gaps, what are some tangible, on-the-ground things that we can do now? For example, small tree plantings of various species. What do you think are some of the next steps in seeing how some of these species fare, and is it a good idea or not?
Oh, that's a hard question, especially for a last question. There are trials like that, you know, facilitated migration or little assisted migration trials, and I think maybe at this point it should just be trials so we can learn a little bit more about what's the species are capable and then what happens when they're moved to areas, but it should be done cautiously. That whole topic is controversial because moving species around is sometimes viewed as invasive species, so there'd have to be a lot of buy-off on something like that. I think in the meantime, with other species that we don't know as much about, just as much monitoring as we can do. We have forest health surveys that are sort of the top-down view, but more plots on the ground. Long-term monitoring plots is probably the key to understanding the changes.
All right, well, thanks, everyone. Just as a final comment, I think, you know, again, to kind of echo what Nick was saying, this diversity of talks really emphasizes how important it's going to be moving forward, that we engage in more collaborative, sort of cross-cutting research and getting people talking between disciplines. I mean, the Alaska coastal current, which we talked about, is a perfect example of that. It's driven by atmospheric dynamics, by runoff from glaciers, and it has impacts back onto the fisheries and also the terrestrial system. So hopefully as we move forward, the Rainforest Center can be an important sort of catalyst for getting some of this dialogue going. I'd like to thank all the speakers again and thank you guys for attending.